Welcome everybody to my talk. I'm really grateful that I'm here. And just one word about this presentation. If you are a Scala developer who is intrigued by deep learning and want to learn a little bit more about it, maybe experiment with it, this is the right talk for you. We're going to introduce deep learning really from zero, as the title says. And at the end, we'll have some basic code examples with Scala. But of course, this also means that if you are a deep learning expert already, this is probably not the right place for you to be. With that said, who I am, thanks Marcin for the introduction. I am indeed a Scala and Akka enthusiast, and also community manager based in Amsterdam, where I run the Reactive Amsterdam meetup. And yes, I also run the Kubernetes Community Days Amsterdam together with some other folks. But unfortunately, this year we decided to cancel it because of these Corona restrictions, and which is why, actually, on this note, I am really grateful to the organizers of this conference, because I know, being a community organizer myself, I know how much work it is, and I know these times are really difficult. So thank you for putting all the work and the energy into organizing this. All right, so our exploration of deep learning starts with a fun planes idea that I want to share the backstory with you a little bit. About a year ago, I was working next to the airport of Amsterdam. So what you're seeing on screen is a Google Maps screenshot of the area around the airport of Amsterdam. And what you can see is historically, this area that is highlighted is the first part of the airport that was built, like 100 years ago or something. And only after, when traffic grew, they decided to add a few more landing strips. And those are the ones. But as you can see, in between those two strips, there is this highway called the A4. And that was already there by the time the second strip was built. So the solution that they found is to build a bridge right there that goes over the highway. And the result is, if you're very close to it, the result is that you have these massive, huge planes that simply stroll over the highway traffic, and the effect is incredible. I'm sure if you've seen it, you must have been impressed as well. So for about 1 year, the view from my office was something like this. Every now and then, you would have a massive plane strolling peacefully just above these little cars and people walking, and I was really super impressed by it. And so I thought, I decided to, I wanted to learn something about AI. And so here's the simple idea: to have a Raspberry Pi looking out of the window, and which is using its camera module, and train a deep learning network to tell me whether in that moment there is a plane on the bridge or not. So here we go. Here's the setup, where we have my little critter Raspberry Pi sitting there in front of the window, and you see the bridge in the distance. And on the right, you can see examples of pictures that it would take. So one there with a plane on top, and the other one below where there's no plane on the bridge. This is a simple idea. And the outcome of this idea is, if there is a plane on the bridge, we're going to tweet about it. And we might enter a risky legal area here, but I actually didn't bother about it too much. I think in the Netherlands, filming objects in public is pretty much a fair game. So so here we go. Now, how are we going to build our deep learning network? First of all, we need to introduce some AI concept and understand a little bit what we're talking about. So from a very high perspective, deep learning, which is really a sort of a alias for neural networks, is a subset of machine learning which itself is a subset of a general concept of artificial intelligence. And if we're looking at the subsets of machine learning and then deep learning inside it, well, these projects are mostly about climbing the pyramid of wisdom. Maybe you've seen this before. The idea of this pyramid is that starting from raw data collection at the bottom, if we parse and organize this raw data, then we transform it into information. Information is readable, is parsable, it's easier to manipulate. And then from this information, we can extract patterns or try to see recurring patterns in this information, which will be our knowledge about this phenomenon that we're analyzing. And finally, we can use these patterns to create some wisdom, which is make decisions about it or predictions. And so a typical application of a machine learning or AI use case is on top. So we're looking at trying to make predictions and generating wisdom from our knowledge. The two cases that are most common for machine learning or artificial, like in general, deep learning cases are two common use cases. The first one is regression. Regression basically answers the questions, how much? So if you look at the graph on the left, this could be for instance, a case of, say, a house price given its square meters. So on the x-axis, you would have the square meters of the house, and on the y-axis, you would see the average, the prices, the measurement you've done of those houses. And then, so the idea is to try and understand, to establish a relation between the square meters and the final cost. In general, we call this linear regression. It means establishing some link and creating a function based on some input. And this is regression. Whereas the second use case, classification, basically answers the question, what kind? So in the picture, you see this famous use case where someone trained a neural network to try and distinguish a Chihuahua's dogs from the raspberry muffin. And I mean, you will reckon that it's not super easy. I mean, with some muffins and some Chihuahuas, myself, I'm not quite sure what I'm looking at first glance. So yes, regression and classification are the two main use cases. So in our case of the planes, it's a classical classification case, binary classification, because we only have two classes. So for instance, on the picture on the left, case where the plane is on a bridge, case on the right, there is no plane on the bridge. This is it. How are we going to build this? Now, the first revelation for me by tackling this project is that really AI and deep learning is still at a stage of trial and error. And this might come as a bit of a disappointment a little bit, but the problem is we only know that for some problems, certain deep learning architectures work better than others. And there is no deterministic way of creating a specific network to solve a particular problem. So in most cases, what you do, you start from some known architectures that have been successful in other cases, and then you tweak it, and then you try again until you get some satisfying results. This is more or less how it works. Really not very far from trial and error. So what are these architectures that we're talking about? In this slide, we can see the type of deep network and the typical use case. So for instance, unsupervised pre-trained networks, they are good at reproducing existing models and real-life use cases, such reproducing sound or reproducing handwriting. You train your network with a lot of handwriting scans, and then the network will be able to replicate it. The second architecture from the top, convolutional neural networks. This is the network that we are going to focus in this presentation, and its absolute best case is image recognition. So faces, animal, street signs, anything. For instance, a self-driven cars like a Tesla probably has a lot of convolutional neural networks inside to recognize all the signs in the street, recognize if I don't know if a traffic light is red or green and things like that. Recurrent neural networks architectures, so the one at the bottom, these are very complicated. It's about processes where inputs have some sequentiality and some chronologic. What do you say that? Well, where inputs over time are linked with each other. So think like speech synthesis, what Google Home or Alexa do. These processes that have inputs that are linked over time, they need to be modeled by these recurrent neural networks, and these networks are super complicated. There's a feedback loop that helps the network learn new things, but also sort of forget old things, because otherwise old things might be too much of a burden on its knowledge. It's really quite complicated. In this talk, we're going to focusing on the middle one, convolutional neural network. Now, before we get into code, we just need then to introduce the basics of this network, these kinds of networks. And the very basic building unit of a neural network is the artificial neuron. And its name comes from our own neurons that we have in the brain, or animal brains. And if you look at it, if you look at a single neuron, it's not all that complicated. The idea is we have a central transfer function which takes a series of weight inputs. So, and these inputs can be one, two, many. And this transfer function will apply some function to this neuron, to these inputs. And the output of this function, a bit confusingly, is called net input. And it's the result of this transfer function. And then this transfer, the output of the transfer function is fed to another activation function. This activation function, basically, it's logic to look at the input and decide whether to propagate this information or not. This is really the basic of an artificial neuron. So, multiple inputs on the left, transfer function. The result of the transfer function is checked by the activation functions, and then we propagate this information or not. And now you may be thinking, wow, this is not all that powerful, right? How does this work? Well, the thing is, this becomes really, really powerful when you combine it with other artificial neurons. And we generate this typical image that you see. It's a multi-layer neural network where many of these neurons are connected to each other. So if we're looking from left to right, what you see is we will have some input values, and then a first layer called the input layer of neurons that typically their transfer function and activation function just make it propagate all the information to the next layer. And then we have a series of hidden layer, in this case it's two hidden layer, which have a variable number of neurons that are all connected to each other in that fashion that you see on the screen. When we traverse all the hidden layers one by one, the last hidden layer is connected to an output layer, which is usually a very few neurons. In our case, for the planes idea, it will be two neurons because we have two classes, but it doesn't have to be two. Just the idea is the last hidden layer collapses all this information into a very simple and tiny output layer, And the output values of the output layer is the result that we're looking for. This is what we're going to look at. So to make an example how this works, let's say if you look on the left, the input values are A, B, and C in this case. Well, the input layer, as we said, will just propagate blindly all the values forward to each of the neurons of the first hidden layer. And then this is where the magic happens a little bit. The functions in the neurons in the hidden layer, in this case, only two of them decide to propagate their information. And then the neurons in the hidden layer 2 also, only two of them will propagate their information. And finally, the output values will be, let's say, 2 and 5. Now, if we change the input values on the left, and so now it's T, P, and G, the input layer will propagate all of them blindly like before, but the configuration that comes from the hidden layers after, according to their transfer function, will be completely different. So now the output values are 7 and 1. And as you can see, if you scale up the hidden layers to thousands and thousands of nodes, and maybe you have more hidden layers than 2, you can have as many as you want, you can see that the configurations are really close to infinite. The possibilities are incredible. And now I can also tell you that why these networks are called deep networks. Because once you have so many hidden layers, and in it you have so many neurons, each of them configured with some different transfer functions, it becomes practically impossible for us humans to understand what's going on there, just because of the sheer amount of possible combinations. One of the reasons why deep learning and neural networks have not been as popular as now before, the concept is pretty old, but it was only made popular in recent years, is because the computational power required to calculate all these possible combinations is enormous, is gigantic. And we didn't sort of reach a computational power that enabled it until very recently. Okay, now that we have a grasp of the power of these networks, let's give a deeper look at convolutional neural networks, which, as I said earlier, are really incredible for image recognition. Now, where does their power reside? What makes them so powerful? Look at this slide. I am 100% sure that as you looked at this image, you immediately knew which one was the rabbit and which one was the cat. Now, if you, though, were asked, what is the process that your brain went through to identify that one of them is a cat and one of them is a rabbit, well, then it's not that easy anymore, because we humans, we just know immediately, like in a snap of a finger, oh, that's a rabbit, that's a cat. But if you try and break it down, what would it look like? It would be maybe something like, so these animals are both black and white. They both have 4 legs, and they both have 2 ears, and they both have like a fur and a tail. But maybe the rabbit has longer ears, and the eyes of the cat are in the middle, while the eyes of the rabbit are on the side. And the tail of the cat is maybe longer, and things like that. And then you go deeper and deeper into these little differences. And your brain, amazingly, it takes no time to immediately do this process. But if you were to teach this to an algorithm or to a computer, you would find it is really, really, really difficult. The power of convolutional neural networks, from here on CNNs, is exactly here. They are able to perform an automatic feature extraction, where if you train a network with thousands and thousands of images, it will somehow mysteriously learn how to identify these features that differentiate for instance, a rabbit from a cat. And this learning is actually translated into adjusting the transfer functions and the weights on all the neurons that compose the network. If we look at this image here, this slide, again, this is just a bit of a rabbit example. What a convolutional neural network does is, imagine you have all the images, a lot of images of rabbits, like the ones above. Now, if you take each one of this image and apply this grid on it, this convolutional neural network can learn some filters that if you apply these filters to an image, that is, you look at this image through these filters will tell you whether there is a rabbit in the picture or not. So now what you see on screen, that image with the grid, is an approximation. But the idea is, if you train this network with thousands and thousands of images of rabbit, and that grid that you see on the left is at a pixel level, so each pixel, then the network learns the rabbitness of this rabbit. What is that makes it unique? And this is, of course, a very coarse approximation, but this is the idea. The network learns some filters that look at an image and understand whether there's a rabbit in it, or whether those features that make a rabbit unique appear or not. And again, these filters really are just different transfer function, or different weights on the inputs of the neurons. Now, once we have established this, what does a CNN architecture, typical architecture, looks like? Remember earlier we had this schema with the input layer and the layers, the hidden layers in between, and then the output. Well, for a convolutional neural network, it looks something like this. There is an input layer that will take basically your image data, and then it's followed by a convolutional layer, and then a subsampling layer, the yellow one. Now, the convolutional layer is the layer that does the job of scanning the image and training these filters that we've talked about. And the subsampling layer, basically, it sort of just reduces the bandwidth of the information that comes out of the convolutional layer. So you can tune it, but in most cases, you basically halve it. So we have then two convolutional layer and two subsampling layers. So at the output of the last subsampling layer would be basically the outcome of these filters, and then sort of reduced in bandwidth to make computation easier, followed by a single hidden layer or dense layer, which typically starts at about 500 fully connected neurons. And these are all neurons, like you've seen, that take 500 input and then collapse it back again into the output layer. And then the output layer will have an output that is based on your use case. And for the rabbit example, it will be something like, I believe that there is a rabbit in this picture, or I believe there isn't, or maybe I'm not sure. This is the typical, very successful architecture that we're going to start with. All right, time for some code. Deep Learning for J is a framework. It's a library that helps you build neural networks. Why I chose Deep Learning for J? I tried TensorFlow before, but I didn't like their Java APIs very much. I think TensorFlow really is born, the TensorFlow APIs are really thought for Python use cases more. And then I tried Deep Learning for J, and I really liked it. Of course, this is just my opinion. Feel free to try everything and find what you like the best. So the first step that we need, if you remember, is training images. What we need to build is a data set where you have images of planes and images of no planes. So both classes are represented. And in my case, of the pictures that you've seen before, I really only want to check if there is a plane on the bridge. So what I will do is for each image, I will crop it down and resize it. So each one of those images is 171 times 25 pixels. There's really no reason why these numbers, maybe there was a reason, but I forgot what it is, but it's just numbers. It could be anything. And then you classify and then you separate them. So you label each image. In my case, in our case, you can just put them in two different directories, a plane directory and a no plane directory. Notice that what's implied here is that you have to classify manually thousands and thousands of images. So I've been looking for months at thousands and thousands of images, and each of them classify whether there's a plane or not in it. So this work is really not to be underestimated. But anyway, once you have your training set, what you want to do is you split this image data set in two. Say 80% of the images will be used to train your network, and the remainder 20% will be used to test your network. So the idea is you want to see how well your network behaves with images that it has never seen before. And now, once you have this training and test set, we are ready for some code. So some settings that we are going to use for our training is, first, of course, we code information about the image, input height and width, which is the pixels that compose our images. Depth is basically each image, because it's a color image, each image has 3 input channels, red, green, and blue. And so depth is 3. And then we'll have the number of possible outcomes, which in our case is 2, plane or no plane. So classes number is 2. And there's a few other settings, but this is really the basics. And then let's build our network in Scala, layer by layer. Now, there is a little caveat that I want to say. The code that you are going to see on these slides is pseudocode. So if you try and if you would copy paste this code, it wouldn't work, because I simplified it to make it clearer and shorter. But the original working code is available on my GitHub repo that we will see a link at the end of this example. All right. In deep learning for J, we start our configuration like this. We create a builder, and then to this builder, we add simply our layers one by one. So if you follow the layers on the top right, the first layer that we put is a convolutional layer. And what does this code mean? When you see convolutional layer dot builder and then 5 and 5, that 5 and 5 is basically the dimension of the filter. So we are going to try and build this filter that looks at the image in a fashion of 5 pixel by 5 pixel. So we will have this filter that sort of scans the entire image, 5 pixel by 5 pixel. The depth you see on the second line is the 3 RGB colors you've seen before. The stride, it means when the filter moves along the image, what's the step that it takes. And this filter will move by 1 pixel and 1 pixel. So it moves by 1 pixel at a time throughout the image. And this convolutional layer will have an output of, we will have a number of 20 outputs. These 20 outputs will be fed to the subsampling layer after. And there it is. The subsampling layer has again, a kernel size and stride of 2. That basically means that we are halving down the output, the information that comes after the first layer. So we add the subsampling layer, and then we add another layer. It will be another convolutional layer, which looks exactly like the first one, only the output will be 50 instead of 20. And after that, we'll have another subsampling layer, again, that halves the information that comes from the previous network. And again, what we are building here is really just an example that looks like reality. There's more things to it, but the concept really is here. And finally, we have this dense layer, which is nothing more than all these neurons connected 500 that will receive the input from the last subsampling layer. And finally, we add an output layer. This output layer will have two outputs, because num classes is two, it's plain or no plain. And then finally, we will have a couple more settings, like the input type that will be given to this network, and those settings reflect our images. And finally, build the whole thing. So I know it looks quite Java-esque. Their deep learning for J also has a Scala API, but I just used the Java base one. But then you see on the left, you have this neural network configuration builder, and the output of this will be your network that then, after you've built it, you proceed to train. And the next page, this one here, is about how do you train it. It's still pseudocode. So again, the real thing is on GitHub. But what you want to do is basically you want to read all these images, you split them in two data sets, the train and test set, like we said before, and then you decide actually when to stop your training. So in this case that we see there, I decided to put a termination condition after 6 minutes. And so you create on the next line your configuration for this early stopping configuration. You decide you need to tell it where to save this model and things like that. But then on the very last line of this slide, you can see that we have this early stopping trainer, which takes as input the configuration we created before, the network model that we created before, and a pointer to all the images. And then we have this magic little word there, fit. This is when the magic will happen and put all the pieces of the puzzle together. This guy will train the network for a few iterations and see, comparing using the test data, will decide which configuration works best. And by configuration, I really mean all the weights on all the inputs of all the neurons. So at the end, you will have the best model that comes out of this training. And I was supposed to do a live show here, sort of, but then coronavirus happened, and so all we get is a screenshot. And it looks like this. As you can see, if you read from top to bottom, you see that this trainer goes through different epoch. And epoch here really means full iteration, means training the network from zero and from until it sort of converges, which means that the weights on the inputs of the neurons stop changing. And so you can see that, for instance, at epoch number 0, we have a certain score. And at epoch number 1, we'll have a better score, which is 0.94. And then we go through all the epochs until we finally reach 6 minutes at the bottom. We've been training the network for 6 minutes. In the 6 minutes, we've done 8 full iteration, 8 epochs. And we keep the best model that gave us the highest score. In this case, what is it? 0.964 at epoch number 5. Yes. So this configuration will be then saved in some file or somewhere that you can use it after. Now, you might be wondering, what is the criteria? What is that 0.95? What does it mean? 0.96 and 94. What is this about? We're going to just check it just in a little bit before when we are going to see the results of this network, the performance. First, before we do that though, I just need to show the entire pipeline, because there is one little bit of reality that we all need to know. There it is. In fact, AI is only a small bit of AI projects. As you can imagine, there's a lot of other operations you need to do to make this happen. So here you see the flows that I had to create. The top flow is about detecting that the plane is there. And so what do I need to do for it? I need to take a picture every minute, let's say, and then trim it down, save it, crop it. And only then I can use, there is an AI bit, which is detect whether there is a plane or not. Then you need to move images to folders, save them to files, whatever. Then the next flow is a Twitter flow, which you want to tweet, let's say every hour, a picture of a plane that you have identified. That means you do, again, a lot of I/O to see which images you tweeted, which one you haven't tweeted yet, and things like that. At the bottom, there is a flow to train the network and evaluate its performance, because the more images you have, the better the network is. So you want to keep training it over time. And really, the only AI bits that you have are the ones in blue. All the rest of the operations is a lot of I/O, and everything. Also, each step can fail, file, CSV, everything. So this is a bit of a of a downer for enthusiasm, but of course, data projects in general require a lot of data processing, and the AI bits, the real fun stuff here, it's only very little. So important to know. The way I implemented all these flows is, as I said, I'm a big fan of Akka, and so this is implemented using Akka streams, which helps us not only translate these flows very well into code, but also has in it all these mechanics to do back pressure and managing failures and things like that. So really, any stream approach will work. For me, Akka streams was a very good choice. Finally, what are the results after we built and we trained our plane network, our neural network that detects planes? There it is. I did create a Twitter account called Planes on Bridge that would tweet every hour a picture of a plane on the bridge. And I had 11 followers. There were all my friends and a couple of fake accounts. So not the most popular Twitter account out there, but the icon of this Twitter account was, I made it, and I was kind of proud of it. And sorry, to make it more fun, I decided to put a random quote from the internet on every tweet. So yeah, it was fun, and in the end, it worked. As you can see, the images, the colors of the trees changed through the season, so that was quite fun. How do we evaluate the performance of our network? How do we see how good the network is? Well, we do this using the confusion matrix. What is this? Well, basically, every time that the network makes a prediction, this prediction can fall into one of these four possibilities. The true positive, that means that there was a plane in the picture and the network correctly detected it. True positive. But then below that, could be also a false positive. So that means the network saw a plane, but there wasn't any plane. You have a false negative on the top right. It means that there was a plane, but the model didn't see it. It missed it. And so it's a false negative. And finally, a true negative in the bottom right corner. That means that there was no plane, and also the model didn't see one. And so true negative. Now, if I observed my network throughout these months where I was tweeting these things, and if I plot it, then it behaved like this. Lots of true negatives, which is something that we expect, because in fact, most of the time there are no planes on the bridge. Some true positive at the bottom, but in fact, if you look at this graph, it really doesn't tell us a lot. I mean, what does this mean? In fact, what you can do from this data to really evaluate the performance better is you can use two measures. There's a few measures, but we're going to look at two in this case. One is called precision, and it's basically the number of true positive divided by the number of true positive plus false positive. Oh, there should be parentheses there. Yes, sorry. Well, in any case, this precision measurement gives us an idea of how well the model avoids false positives. So, in other words, how well the model, when the model sees a plane, it's probably there. We are good at avoiding false positives. And the recall instead is the sum of the true positive divided by the sum of true positive and false negatives, which basically tells us how well the model avoids false negatives. So if we look at the graph, our precision over time of the network that I trained is pretty high. So that means that when my model sees a plane, the plane probably is there. But the recall, the score in red on the graph, tells us that our model also misses quite a few planes. I mean, when there is a plane, the model doesn't always see it. So that's a false negative. And also, you can see that the value of these two is very variable over time. And so you might wonder, when does it go wrong? What makes it go wrong? And well, the answer, living in a Northern European country, is mostly the weather. So you see, there's all kinds of examples. There's foggy, and so a plane is difficult to see. When it rains, there are drops of glass on the window, so they mess up the plane image. Or in the bottom left picture, the sun is kind of setting, so it's just facing the camera, and so all the colors are messed. The contrast is very high. But if you squint your eyes, actually, in the bottom left picture, there is a plane. Really, you just need to look a bit better to see it. Oh, and also the bottom right image, there's only a part of a plane. And so again, our brain, of course, there is a plane on the bridge. But if you think back, a convolutional network has learned some filters that detect a plane. And then maybe one of the filters is about the front, the face of the plane, and it's not visible here. Maybe you'll have another picture where you don't see the tail. The tail seems to me very important. It's like sort of this triangular shape. And if you don't have the tail in the picture, probably the network has more trouble. I don't know. For me, looking at this and learning through this thing, it really makes me realize how powerful our brain is. I mean, it's mind-blowing, right? I mean, we see half a plane, and we know that there is a plane. But for a network, it's a lot more complicated. Anyway, and then there is one, I'm almost done here, but there's one last concept that I want to briefly touch upon for the performance of this network, and it's AI bias. You've probably heard about AI bias before. Maybe you remember the terrible examples from Google or Microsoft where AIs were trained and they had some racist connotations built in, and AI bias is everywhere. And even in a silly, playful case like mine, because I am based in the Netherlands and the air company of the Netherlands is KLM and the planes are blue, well, then my network has been trained with a lot more blue planes than other planes. So what happens is that when the network sees an image with a blue plane, it'll be like, oh yeah, sure, I see a plane, no problem. But then a plane that is maybe white or another color, the network has a lot more trouble seeing it. And again, AI bias is everywhere. Training a network, even with this playful project, training a network with a homogeneous, sort of unbiased training set is very difficult. And I think going forward, this is one of the major challenges of AI in general. Now, what are the next steps for you? If you're curious, well, just find a fun use case and a data set. If you want to start with my data set, go ahead. It's there on GitHub. Learn a few more details about AI and CNNs. What we've done here was an overview. There's a lot more to learn about it. And then I would suggest try and find a use case in the domain where you are working on. Maybe you are working on some company that does, solves some problem. Maybe there is room for a deep learning, artificial intelligence use in it. So just look at your own domain first. And if you need any help, there is this very welcoming community about AI and machine learning in Scala. The link is there on Gitter. As a reference, I actually used this book to build my knowledge about deep learning, which is, this book was published in 2017, so not very, very recent, but the foundation hasn't changed. It's very, very solid. And there's a couple more links there at the bottom. And this was for me. Thanks for attending. I hope you enjoyed the talk. And yes, please, everybody, stay safe during these difficult times. Thank you very much.
Okay, Fabio, thank you very much. That was a very interesting talk. So we have a couple of questions. We actually have two questions from Rahul. So first question is about the performance of training and detection. So
yes,
do you know anything, and how could you compare the performance with respect to timing for training and detection between Python implementation, Java, Scala, and maybe C++?
Oh, yes, that's a really good question. To be honest, I haven't done this. I didn't compare. I only, I'm a real Scala fan, so I really went down and did this with Scala directly. But in fact, TensorFlow, for instance, is just a sort of wrapper on top of C libraries or C++ libraries. Also, my network is not a very good example for performance in training because my data set was pretty small. It was maybe about 14,000 images, which it's pretty small compared to the real images. So I'm sorry, but I don't have any any answer about this.
I see. Okay. The second question was actually quite related to the first one, because it's about whether for the same library using different language interfaces, do you know if there are any effect on model accuracy? But I guess you haven't heard it.
Yeah, cool question too. So what I have done, let me go back quickly to the, like here. So, well, if you look at this result on the left, it's very Java-ish, right? All this builder and mutable state in it. There is a Scala wrapper, as I said before, but I don't know. I didn't, to be honest, I didn't test it because I tend to try and stick with the base one. Maybe you have the risk that the Scala wrapper then stops being maintained or something like that if it's not officially supported. And so, again, I've only tried the Java version. I can't really say anything more about this. Yeah, sorry. 2 questions and 2 things I couldn't really answer. Sorry about this.
Still,
Do you have any question that I can answer?
I have one question from myself, which is for these false positives. Did you have any interesting situations, like, for example, I don't know, maybe a bird misclassified as a plane or something like that?
There have been a couple of fun use cases. Really good question, where there would be a plane flying in the background. So instead of just like strolling on the bridge, there would be a plane flying just above the bridge in the distance, just landing on the airstrip. And when that happened, it was always super funny because sometimes the network would see it, but sometimes it wasn't sure. Because so the network, what it does, what it outputs is probabilities, really. So when it sees an image, it doesn't output like 1 or 0, but it tells you, I am 95% sure that there is a plane, or I am 95% sure that there is no plane. And then in these cases, when there was like a plane flying in the distance, the network would be like, I am 60% sure that there is a plane, but also 40% of me thinks that there is no plane. I'm not sure what's going on. And so, yeah, after a while, your network really becomes your child a little bit. And so, yeah, there's been a few funny use cases. Yeah.
All right. Great. Thank you very much, Fabio. Thanks again.
Thank you for having me.
Yes, that was a really great talk. So for anybody who's interested in deep learning in Scala, please follow the links. And yeah, and you can also ask questions to Fabio in our Q&A session.
Yes, I'll be on Slack.
Yes, so Slack and Zoom, of course. Now we would like to invite all of you for a networking session, which is going to be officially announced soon with all the informations. It's going to appear on Slack and also on the information board that will be displayed here in the stream. Official announcement will take place at 10, so shortly. So yeah, see you everybody, and thank you, Fabio, again.
Thanks again.